capturing waveforms and analyzing them with an SDR platform like HackRF1. So right now, my HackRF is tuned to 3.625 gigahertz, which doesn't sound very good. Let's go to 315 megahertz. And let's just punch something in here and see what happens. I'll set peak hold, so now you get this green line across the top of the frequency domain plot there. So that's just telling us what's going on within this range of frequencies around 315 megahertz. If I type in 0000 lock, oh, you might not be able to see it, but something kind of wiggled around the middle of the screen. I'm going to try to zoom in a little bit. Maybe I'll go to 314.5 megahertz, and I'll just narrow my view. I'll set my sample rate to 2 million samples per second instead of 8 million samples per second. So now I'm looking at only 2 megahertz of bandwidth instead of 8 megahertz of bandwidth. And now 315 is over here. If I enter in a code and press the lock button or unlock button, there we go. We can clearly see the transmission. And one trick I like to do to verify that what I'm looking at is really the device in my hand and not something else around me is I like to transmit really close to the receive antenna. And if I do that, you see how that got a lot higher? Easy way to verify. If you have physical access to the transmitter that you're trying to reverse, easy way to verify that what you're looking at is in fact, what you're looking at in software is in fact the thing you have in your hand. It's just to hold it at point blank range, and you'll see the power level spike like that. So this looks to be like about 314.98, a little bit under 315 megahertz. And some error is expected, especially in lower cost devices. They might have more frequency error. It's authorized to operate at 315, but it's off by a little bit. It's not enough to be concerned about, but knowing that precise frequency of operation can actually help us later. Now what I'm going to do is make a capture and save this capture to a file. And it's very easy to do that by pressing this record button in the lower right hand corner. So I'm going to enter a code, 0000, and then I'm going to hit the record button and then press the lock button so that it transmits, and then I'll stop. So I get a nice short recording that has my transmission. So I hit record, I press the lock button, it transmits, and it's done. I hit the stop button, and now I have this file. I didn't change its default name, but it's saved here in /temp. So I should be able to see that. I've got this file. It's this one. 314.5 times, 3.145 times 10 to the 8 power. That's the frequency. So I have this one here from earlier too that I will remove so it doesn't distract me. And I'm going to open up this file in a tool that I like called Inspectrum. And Inspectrum is a tool for visualization of radio signals. It's a newer tool. It's open source software, and it gives me a spectrogram. A spectrogram shows me time on one axis and frequency on another axis, and it shows me kind of everything that was going on in that chunk of spectrum during the period of time that I was recording. And in this case, it shows me time on the horizontal axis and frequency on the vertical axis. So this bright green line across the middle corresponds to that spike that we saw in the middle of the frequency domain plot in Ossmann FFT. So basically, we took that plot, we turned it sideways, and now we have a whole bunch of information here in 2 dimensions instead of just looking in 1 dimension. If I scroll over to the right, you see here now I have an event that I can scroll around and see what's going on. And so higher frequencies are further up. So here, this center frequency here, this green line is 314.5 megahertz. That's what I was tuned to. And up here is 314.98 megahertz, where we detected this. And I can zoom in on this a little bit, kind of horizontally zoom. And And you can see that this event is made up of individual pulses. Kind of look like an I beam or something, or like a capital letter I turned on its side, because there's a little bit of kind of frequency spreading when there's this abrupt on-off transition, this signal is turning on or off. But you'll notice if you look horizontally, if I scroll through here, you see how everything is all lined up horizontally? They're all at the same frequency. Every single pulse is all at the same frequency, which tells me this is not a frequency modulation. But the amplitude changes. The amplitude is represented by the color. And the color goes from this blue background color to this green color when there's an active signal. It abruptly turns on and off. So this modulation I can easily identify visually as being on-off key, which is kind of the extreme form of AM. It's turning the amplitude of the radio transmitter on or off. And I can also kind of tell that it's made up of these distinct pulses. If I go starting at the beginning, you can see there's a very consistent pattern at the beginning of a packet, which is a pretty common thing to see, because it's just kind of giving the receiver some time to wake up and to synchronize to these symbols, but it's not really transmitting any information yet. It's just transmitting what we call a preamble. But if I keep going to the right, then we start seeing some pulses that have different durations. There are long pulses, and then there are short pulses, and then we get some long pulses, short. It seems that we're going back and forth between two different lengths of pulses. See that? Some of them are short, some of them are long, but everything seems to be one length or the other. And Inspectrum gives us kind of a handy tool to measure these things. I can turn on this enable cursors, and then I can measure the time durations, and I can divide this up into a number of bits or symbols. Let's say I want to go like, I don't know, 10. Then I can kind of move this cursor around so that I can see, look at that. There's a very consistent period of time from the start of one pulse to the start of the next pulse. And it doesn't matter whether the pulse is long or short. And so I'm starting to get the idea that this is a constant rate pulse width modulation built on top of on-off key. Pulse width modulation means that pulses of one length represent a 0, and pulses of a different length represent a 1. And so I just have this long string of pulses that represent some string of 0s and 1s. And I can measure the bit period here. I can kind of see how long it is by using this little cursor feature. But I also like to kind of subdivide these pulse periods to see what's the smallest time unit that kind of lines up with the beginning and ends of these pulses. So if I double or triple my number of bits, I can kind of see, maybe let's try tripling it. Hey, look at that. If I triple it, do you see how every single pulse period is kind of made up of 3 time units? The long pulses are on, off. 2 on, then 1 period off. The short pulses are on, off. 1 on, and then 2 off. And it's very consistent like this. So I'm going to call these 1/3 of a pulse period, I'm going to call this 1/3 time unit a symbol. And I'll just say that if I were to read this as symbols and say that an on is a 1 and an off is a 0, then this section that I have highlighted here I would read as 110, that's a long pulse, 110, that's a long pulse, 100, that's a short pulse, and so forth. So I have this string of symbols, 110, 110, 100, 100, 100, 100, 100, 100. And this is how I'm going to configure my yardstick 1 to interpret this waveform, is by configuring it to a symbol rate. And I think I actually have a bug here. Oh, you know what? I forgot to tell Inspectrum what my sample rate was of my capture. So if I tell it that I captured at 2 million samples per second, then it should be more correct. there, you can see that it's about 2,450 bits per second. That's what in Spectrum calls a bit, based on the period that I have specified here. Really, I would call that a symbol, right? I have 3 symbols per bit, and my symbol rate is about 2,450 symbols per second. So it's about the speed of a 2400 baud modem. Okay. So now I know the precise operating frequency. I know the symbol rate. I know the modulation is on-off keying. I've learned all those things using SDR tools. And notice I didn't have to write a single line of code. I didn't have to use any great knowledge of digital signal processing. I just had to know a little bit about how to use these GUI tools to interface with my HackRF, capture a waveform, and analyze it visually. And I've learned all these things. This is where I'm going to turn away from SDR and try to use these parameters to configure my yardstick 1 to do kind of the next steps of the job. I seem to have forgotten one of my antennas, so I'll just transfer my antenna over the yardstick 1 and plug this in. And now I'm going to use those parameters that I figured out to configure the yardstick 1. And yardstick 1 is used primarily from a piece of software called RFCAT. RFCAT is some software made by Atlas, and it's specifically designed for this kind of work. And yardstick 1 ships with RFCAT firmware, but RFCAT also has a host-side component that gives you a Python interface. It's easiest to use this interactive Python shell based on IPython. And so it gives me a thing called D, which is my dongle, or my device, my USB device. And I can do things like set the frequency. And I'll set it to 314.980.000. So that's the frequency in hertz that I observed using Ossmann FFT. And then I'm going to set the modulation. And I'm actually going to use this one, modulation ASK or OOK. That's one setting that implements either amplitude shift keying or on-off keying. We observed on-off keying, so that's what I'm going to use. I'm going to set the modem data rate. There we go. Tab completion for the win. I'm going to set that to 2450. Remember, we observed 2450 symbols per second. So I set those, and those are the main things I need to set. Now, I think I'm going to not have success here picking up this packet, but let's just try it and see. If I do an RF listen, now, okay, you get a bunch of garbage, but let's see what happens when I actually transmit something. Transmitting, and notice we're not seeing any packets received. We're not seeing anything other than this garbage that happened when it first started up. Let me transmit again and see if it does anything. It doesn't do anything. The reason it's not doing anything, probably the main reason, is because what it's trying to do is, there are two reasons. One is that it's expecting that a packet starts with a preamble. By default, the wireless transceiver chip that's on the yardstick 1 expects to see a preamble of alternating symbols at the beginning of the packet. So it's expecting to see on, off, on, off, on, off, on, off, or 1, 0, 1, 0, 1, 0, 1, 0. And we don't actually have that. If we look back in Spectrum, at the beginning of a packet, what we had was not 1, 0, 1, 0, 1, 0. What we have is, in fact, well, I don't have this quite set up right, but what we have is 1, 1, 0, 1, 1, 0, 1, 1, 0. We have a waltz instead of a two-step, and that is not going to satisfy the yardstick 1's notion of what a preamble looks like. So what I need to do is tell it to turn the preamble off. And the command here is packet preamble quality threshold. I'm going to set the preamble quality threshold to 0, which says ignore the preamble. Don't expect 1, 0, 1, 0, 1, 0, 1, 0, 1, 0 at the beginning of the packet. And the other thing I need to tell the yardstick 1 is what to look for to detect the beginning of the packet. What pattern of bits should it expect? It has a default setting that is the default in the CC1111 chip, which is kind of silly because usually you almost always have to set this. So I'm going to set the modem sync word. The synchronization word is the sequence of bits that it's expecting for the beginning of a packet. Now, ideally, most radio communication systems that have a preamble of alternating ones and zeros, most of the time what you see is they're 10, 10, 10, 10 for some length of time. And then they have a synchronization word, which is a sequence of bits that is not just alternating ones and zeros. It's something that has good autocorrelation. It's something that every packet starts with. You might call it a starter frame delimiter. Sometimes it's called an access code or a synchronization word. In RFCAT, we call it a sync word. And so I'm looking for something to identify at the beginning of the packet. Well, I haven't really identified that yet. I haven't identified that there is a fixed sequence of bits that this thing sends after the preamble that is very consistent. So for now, I'm just going to actually set my sync word to the beginning of the preamble. And so what I should see, if I kind of look a little further here, what I should see is 110, 110, 110, 110. But I don't want to match just anywhere in this Waltz preamble. I want to match the beginning, so I'll put a few zeros at the beginning of it. I'll do something like, let's say, if I put it in binary, I could say 0, 0, 0, 0, 0, and then 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. Let's see, do I have 16 here? That's, is that 16 bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Got one too many. And maybe I should take one off from the beginning. So I have 16. Let's see how that works. Sometimes I like to put these in hex, but sometimes it's nice to specify them in binary. This is what it looks like in hex. It's not showing me the leading 0 there, but I've got DB6. So what I'm matching here is nothing prior to the packet, and then my preamble. That's what I'm configuring the yardstick 1, or I'm configuring the CC1111 on the yardstick 1 to look for, to detect a packet. So now let's try that RF listen. And I'll type 10 or 0000 and then lock. And hey, look at that. Now we're getting something. And do you see how we get a lot of the same stuff over and over and over again? Like DB6, DB6. That's because the number, if you think of those numbers hexadecimal, DB6, that's actually, or 6 dB, wasn't that what we set our, look at that, DB6 is what we set our preamble to. So every time you see DB6, that's like part of the preamble, or it's a section of the packet that looks like a preamble. And so we're seeing a lot of repetition, which is interesting, and we're seeing a bunch of stuff that happens every time I push a button. So this time I'll try something else, like 1, 1, 1, 1, unlock. There we go. We're seeing a lot more of the same kind of stuff, a lot of the same hex digits showing up. And it transmits quite a bit every time. And this kind of agrees with what we saw in Spectrum. If I zoom out here, you can see that a lot happens just from pushing the button once. Here's this preamble, and then some bits, and then there's a little gap, and then another preamble, and then some bits, and a little gap, and another preamble, and some bits, and a little gap. And if I were to compare this, I probably notice that it's really transmitting the same information over and over and over again. And that's just a crude way of dealing with unreliable radio communications, right? Like, they could use some sort of sophisticated forward error correction or something, but they don't. They just send the same packet a whole bunch of times in a row and hope for the best. And so, that's a cheap and easy way to improve the reliability of the radio system. So, so it's not surprising that we see a lot of repetition here. Now, I'm not actually a terrific Python programmer, but you know, I'm kind of okay with VI. So I often do things like this. I'll go like copy and paste a hex dump into VI, and then look for patterns. Like I'll search for this pattern, and look at that. You see how I get like the same pattern 3 times in the file? Now how far into this, this is the, if I look at my counter at the bottom right, 250 characters in, I get a repetition, and the next one here is at 499 characters in, right? So I have kind of a consistent, every 249 characters, there's a repetition. So I'm seeing that what yardstick 1 is detecting as kind of one packet is really multiple repeated packets. And if I were to use that information then to go in and configure yardstick 1 with a packet length, or I think it's make packet flen, I think it was 30 bytes long, and then I would do an RF listen, and now it's giving me kind of shorter packets. It's a little hard to read because I'm wrapping around the screen, but some of these should look identical. Now I'm gonna use kind of a trick that I like to do with RFCat, where I'm just gonna kind of packagely just edit files in my RFCat directory, which is kind of silly. But one of the nice things I like to do with RFCat, because it's an IPython interface, one of the nice things I like to do is make a little Python program